In this lesson, we are going to be talking a little bit more about measures of center, basically comparing means and medians to see when we should use each of them. So our first example here, this is actually from our book, which we don't ever use, but this is coming from our book. It's the salaries of the Los Angeles Lakers from 2002 to 2003. That was back when Kobe was still there, but Shaquille was there also. So if you take a look at those salaries, we're going to find the mean and the median. So I'm going to actually use my calculator for that. And I went ahead and I plugged in, when I go to Stat, Edit, I plugged all those salaries in already. So 23.6 million, I plugged them in as millions instead of putting all those zeros. So this would represent millions. And to find my mean and my median, I'm going to go to Stat, Calculate, and then one variable statistic. So I hit Enter there, hit Enter one more time, and you'll see that my X bar there is 5.1. So I know that my mean is 5.1, so that's 5.1 million, right? So I'm going to plug in the mean for the Lakers salaries is $5.1 million. That's the average salary they're giving their players that are on the roster. Now let's find the median. So when I look at my calculator, that median is down here in that 5-number summary, right? Median is 3.35. So when I go here, my median is 3.35 million. Now you'll notice here, that's a big difference, right? A lot of times our mean and median can be similar. In this case, they are off by almost 2 million, 1.8 million about. So why are they so different? That's the question. Well, hopefully you recognize that there are a lot of players making 5 million and less, and then there's Kobe and Shaq. If we were going to calculate, they might be outliers, right? If we were going to calculate it out. So the reason the mean and median are so different is because we have some outliers, mainly Kobe and Shaq. So outliers affect one of these more than the other. If you take a look, it's in your next one, it says outliers strongly affect the blank but not the blank. Which of these numbers do you think was really affected by the fact that Shaquille makes 23.6 million and Kobe made 12.4? The average, right? I mean, those really swayed the average because they're so much bigger. I mean, if you take Shaq's salary versus this guy right here that makes $1 million, Shaq makes 23 times his salary. That's a big difference, and that's going to really pull your average. So we will say outliers strongly affect the mean, but not the median. So if you know your data is skewed, so when the graph is skewed, the mean will be pulled in that direction, the direction of the skew, and the median will not change much. Now what this looks like is we can have several graphs here, right? Here's an example of a left skewed graph. Here's a bell-shaped symmetrical graph, and there's a right skewed graph. I draw these really poorly. I think I'd be better at this. There we go. There's a right skewed graph. So now I really just don't like how these aren't very skewed. Let me make them a little more skewed. There we go. Left skewed, right skewed. That's maybe a little bit better. So what happens is I'm going to make my green line, oops, that's not green. How about my blue line be the mean, and my green line is the median, okay? So in this example, the symmetrical, here's my mean, and if it's really symmetrical, there's my median. They're in the same spot. If it's truly symmetrical, my mean and median would be the same number. Now in a left skewed, which is what this one is, right? This is a left skewed graph. My mean is pulled in the direction of the skewness. So if this is my median, let's just say, where would my mean be? It'd be pulled in the direction of the skewness. So my mean is to the left of my median because it's left skewed. If I'm right skewed, which is what this one is, right? And I put my median, let's say right here, my mean again is pulled in the direction of the skew. So there's my mean. This is my median. So if you were asked to pick that out, hopefully you could, that the mean is pulled the direction of the skew in symmetrical. If it's truly symmetrical, they'd be the exact same number. Salary and money graphs are almost always skewed which direction? Well, let's think. Do more people make, let's have a little graph here. Here's $0, here's a lot of money. Do more people at a company make a lot of money or not so much? Think of anywhere you work. Let's pick McDonald's. A lot of the employees, being high school students, probably don't make a great amount of money, do they? They're minimum wage. Most of their data values will be right here. There's a few employees who've worked there longer who make some money, and then maybe there's the manager or the owner. They make the most money. So you look at this data. If I was going to sketch its skewness, this is right skewed. So salary and money graphs are almost always skewed right. And then the last thing we're going to talk about is we use one of these to describe symmetrical data. If we're going to look at symmetrical data, since mean is not affected in a symmetrical data, so anytime data is symmetrical, we want to use the average. That's the best thing to use. And the standard deviation is really good if our data is symmetrical. So that would be like our bell-shaped curve. So this is an example of symmetrical. So when we have a bell-shaped curve there. And when we have skewed data, so whether that is left skewed or right skewed, anytime we have skewed data, we would choose to use the median if we were going to choose something, because the median is more reliable than the mean, because the mean gets pulled the direction of the skew, right? And we also would choose to use the 5-number summary and our box plots. So those are really good to use for skewed data. So if I asked you what's best to use for this bell-shaped data, you're going to use a mean and a standard deviation. If I ask you what's best for skewed data, you're going to use the median, the 5-number summary, and the box plot. This one says, if the standard deviation of a list of numbers is 0, does that mean that all the numbers on the list are the same? Why or why not? Let's think again what standard deviation means. Standard deviation, I'm just going to pick a little group of numbers here. Standard deviation is how far we are from the average, right? So that's the distance from the average. So if I was going to find the standard deviation of this, I'd have to first find my average, right? So 2 plus 4 plus 6 plus 8 plus 10, and divide by 5. And I get, oh, look at that, my mean and median are the same. This is my average, my x-bar. And I made my data very symmetrical, didn't I? My standard deviation is how far away a data value is from the average. And so I'd go through and I'd take, okay, 2 minus 6, get that number, I square it, I add them all up, and I can get my standard deviation. So how could I possibly, since standard deviation is the distance away, how can I possibly have a standard deviation of 0? What does it mean to be a 0? That means that how far away the data values lie from the average, so how far these numbers lie from this one, is what? 0. If there's no distance between them, they all have to be the same number. So yes, that is what it means. If my standard deviation equals 0, that's telling me there is no spread. There is nothing changing from one to the other. So all numbers must be the same. Alright, so now we're going to take a look here and see how we'd use these different things. It says at Company A, each employee gets a $1,000 raise next year. At Company B, each employee gets a 3% raise next year. What will happen to the mean and standard deviation of each company's salary? So in Company A, we're adding the same amount every year. In Company B, we are timesing by the same amount. So we're multiplying by that 0.03. So if we look at all of the values we have, here's their original salary. So, and then here's Company A is doing, Company B. So these are the new salaries they will get after this. And you can see some of them are getting a better salary, right? If you are working on percentages, the more money you make, the more of a raise you get. So when your boss gives everyone a $500 raise, if you've been working at the company the longest, you're kind of losing out because you're making the most money probably. If you're a new employee and not making the much, you're kind of gaining, as you can see here. See, this is the same amount. All of us got $1,000, but look at what happens here. The 3%, they lose out $100. But everywhere else, they're making money on that 3%. So most employees would prefer to get paid by a percentage and not a set amount. So now we're going to see what happens to the mean and standard deviation. So we're going to find the mean and standard deviation for all three of these. So I want you to do that quick. Pause the video and find the mean for this column and standard deviation. So I want to have x bar for this and standard deviation. Find the mean for this one and find the mean for this one. So go 3 different sets. So pause the video, and then when you come back, we'll go through that. So hopefully when you did this, for my salary originally, I found the mean, so my X bar, to be 58,333.33. And then the standard deviation was 24,832.77. Company A then, so by adding that $1,000, their mean is 59,333.33. So what happened to that mean? From just adding $1,000, what happened to the mean? Well, when you add $1,000 to the salaries, your mean changes by $1,000. My standard deviation, the exact same. So I think right now we could say for company A, and this would be a rule we can come up with, when you add, and really we're going to say or subtract, so when you add an amount, the mean changes by that amount. Standard deviation doesn't change. So that's what we just found out here. That's one of our properties for this. So that's what we found out from company A. Let's see how the mean and standard deviation are affected by multiplying by the same amount. So when I multiplied, which is what company B is, I got a mean of 61,083.33. And then when I found my standard deviation, I got 25,577.76. So what happens here is my mean for company B, when I multiply or divide, my mean and my standard deviation change by the amount. So by 3%. They both changed by 3%, and you can double check that. So that's kind of the property we look at. This is called transformation. So when we want to transform data, because you get a raise or something changes and everyone changes by a certain amount, a set amount, mean changes, standard deviation doesn't when you're adding or subtracting. Multiplying or dividing, they both change. So our last example we're going to do, this is us trying to match graphs. So we're going to match which of these graphs looks like it has a mean of 6.6, median of 6.8, and a standard deviation of 1.3. So the one that has the mean and median the closest would be our most normal one, right? Like here, these are pretty close. So that looks like that could be a normal graph, and these are pretty close. These are not close at all. And remember, the mean gets pulled in the direction of the skew. So since 3.75 would be here and 6.6 is here, I'm going to say that this graph is right skewed. Do I have a graph that's right skewed? Oh, I do, right? Right here. Look at that. The only one that's right skewed. The other two look pretty symmetrical. So they kind of match A and B. So C is definitely the first graph. I didn't even look at standard deviation. I could tell that just by the mean and median. Now, A and B, their mean and median are so close, I'm not really sure which one belongs with graph 2 or graph 3. So the next thing I would look at is the standard deviation. Remember, this is the spread. So when my standard deviation is small, my values will be clustered together. They're all kind of close. The bigger the standard deviation, the more spread out my graph might be. So which graph looks more spread out? Because that would have a higher standard deviation. And I'm going to go with this one. This one's got some gaps. There's a more spread going on here. So I'm going to say that graph 3 matches this because of the spread. This one has a very low standard deviation. See how these are all kind of clustered together? No gaps. So that's graph 2. So hopefully you're going to be able to match these graphs to different things too, just by what we've learned today from that. Tomorrow you're going to have a worksheet and an objective. So if you have any questions, make sure you let me know when you come to class.